Hi, everyone. Welcome to the CGS Technical Webinar Series for the YP Committee. Um, today, Today's presentation will be based on the identification of permafrost features in the Canadian landscape using aerial, satellite, and LiDAR hillshade images. The presentation will provide an introduction to identification of permafrost features in Canada. Before I introduce today's speaker, I just want to remind all of you to put your questions in the Q&A box and not in the chat, as I won't be checking the chat. Today we have Lynden Penner. Lynden has been consulting for over 39 years and is the president of J.D. Mollard and Associates Limited in Regina, Saskatchewan, covering a broad range of terrain analysis and applications across Canada. He earned undergraduate and graduate degrees in geological engineering from the University of Saskatchewan. Lynden has published 34 technical papers and has presented numerous workshops and seminars on air photo and satellite image interpretation for terrain analysis, engineering, and environmental applications. Lynden is currently a sessional lecturer with the Faculty of Engineering at the University of Regina, where he and other members of staff teach an undergraduate course in terrain and site analysis. He is a past president of the Regina Geotechnical Group and is currently a board member for the Canadian Foundation of Geotechnique. Lynden recently received the ACEC SK 2025 Lieutenant Governor of Saskatchewan Meritorious Achievement Award, recognizing his professional accomplishments in the consulting industry. Congratulations, Lynden, for that. And I'll pass it on to you.
All right, thank you so much for that introduction, and hello to everybody there who's joined us. Very much a pleasure to be with you this afternoon and to speak to you about identification of permafrost features. My career in our firm specializes in terrain analysis in its origins under the leadership of Dr. Jack Mollard. It began as an air photo interpretation firm, largely focusing on mapping landscapes and terrain using stereo air photos. Since then, of course, we utilize satellite imagery, LiDAR images created from LiDAR data, and other types of visual data sets, as well as field studies. So the focus will be largely on how we can identify the presence of permafrost in various types of imagery, and so we'll get started with that. It looks like I can advance the slides this way. I've got three sort of general categories or general things I'll be discussing. I'll begin with some definitions, some maps and discussion of the sort of distribution of permafrost across the country, and say a little bit about the timing of permafrost formation. Then the bulk of the slides that I'll run through are examples of some of the different permafrost features that can be identified from various types of imagery and used to identify that there is permafrost present in an area and some characteristics of it. And I'll conclude with a couple of case study examples too. One from an area near actually at the southern fringe of the permafrost zone, and another in the continuous permafrost zone. So in terms of definitions, permafrost is earth material, soil, and rock, which includes the moisture, gases, organic material within those materials that remain at or below 0 degrees C for at least 2 consecutive years. And so to confirm the presence of permafrost, you need to confirm that it stays continuously frozen for 2 consecutive years. It does not require ice. It's based on temperature, but ice within permafrost is common. The frozen layer persists throughout the summer, and the upper layer The upper portion thaws seasonally, and that's what's called the active zone. So there's a sketch here on the right where it's frozen from the surface down during the winter, but in the summer there may be thawed, an active layer where the ground thaws to some depth, depending on where you are and how what temperatures are like, perhaps down to 1 or 2 meters of thawed ground, and that's the active zone. And of course, permafrost forms where the mean annual air temperature is below freezing. In some cases, there is an area of unfrozen ground below the active layer and above the permafrost table, and that zone is called talc. I've included some links here. There's the Canadian Permafrost Association is a great resource for finding out information about permafrost with a glossary of permafrost science and engineering, an illustrated dictionary of permafrost, which has just been released recently, and the Natural Resources of Canada also have some resources. So those are some other places you can go to find information about permafrost. In terms of distribution, Natural Resources Canada has published a permafrost in Canada map, and it looks like this. And so the gray area is the non-permafrost zone. The yellow, which is isolated, less than 10% of the area is frozen. Sporadic, 10 to 50%. Discontinuous, greater than 50%, and then continuous is, of course, 100%. To give you an indication of what that sort of looks like regionally, there's showing a cross section from Kaglucktuk down to Hay River, giving it an indication of depths of permafrost, which can extend to hundreds of meters in the continuous permafrost zone, thinning and becoming more intermittent as you go through the discontinuous, extensive discontinuous, sporadic, and then isolated patches of permafrost. So depending where you are in the country, this is a good resource to get an initial idea of the likelihood of encountering permafrost within a particular study area. The thermal gradient looks something like this, where in the active layer, the temperature can range from several degrees above zero to several degrees below zero over the course of a year. And then as you go down in depth, you reach a point where there's zero annual amplitude, zero difference between the seasonal temperature and then the permafrost table, the base of the permafrost, is where that gradient crosses over into the positive temperature zone. And so that's, and then the average annual ground temperature would be, of course, between these two curves, maximum and minimum temperatures. And this is referred to as a trumpet diagram, if you can imagine. Sort of the open end of the trumpet pointing upwards, and the going temperature increasing slightly with depth until you're below the permafrost zone. Ground ice. So as engineers, this is one of the real critical factors in permafrost, which make it particularly sensitive to to disturbance, to engineering works, is that if there's a large volume of ice within the permafrost, then when it thaws, of course, that ice turns to water, and there's a very large change in volume and subsidence that's associated with that, and very poor engineering conditions. And so the ground ice can be microscopic. It can be within the soil pores, or it may be visible as discrete bodies of ice. And so these photographs were taken in northern Manitoba, adjacent to a hydroelectric reservoir. And so you can see quite a thick zone of ice with some debris within it that is actively thawing. And I'll show you another slide of that area later. and within an organic terrain, where you can develop these very discrete layers of segregated ice, which can be millimeters thick, centimeters, or many even tens of meters large bodies of ice, and so that's really one of the key factors to look at is um, whether or not it's not just permafrost, but is it ice-rich permafrost. Timing of formation. This is an interesting topic that I just came upon some information here recently that related to a project I was working on. Of course, the glacial maxima was something like 22,000 years ago, and then as the ice receded, the landscape and there was warming, and the landscape became ice-free. There was thawing of the ground, and so the some of the permafrost that we see is remnant permafrost from these glacial conditions, and other permafrost formed after the deglaciation. And so we see a map here by Dyke, roughly the same period, a little bit later, 18,000 years ago. And then here's a map showing the remnant of ice that remained at about 7,800 years ago, with glacial Lake Agassiz and Ojibwe out in front, and the ice separating the marine waters from Hudson Bay. So we see, if we look at sort of the last 70,000 years or so on this type of millennial scale, which was during the glacial period, we see these rises and falls in temperature, and the lower O18 values correlate with colder temperatures, and the higher with warmer temperatures. And so we have these cold periods that are roughly 10,000 or so year cyclicity, leading to the younger Dryas cold period, which just preceded the deglaciation in the Holocene, starting about 12,000 years ago. And so during the glacial period, there's quite a broad range of fluctuation in temperature, and then since the warming following the younger Dryas, the temperatures have been much more stable. What caught my interest was a paper by Tabitha Raman and Pascal Roy-Lavalle recently, looking at dating ice within ice wedge polygons in the Churchill Basin, the Barrens of northern Manitoba. And they found that the ice within these ice wedges is quite recent, in the order of 250 to 700 years ago is when that ice formed, which is in the permafrost. And so within this window here, which is about 12,000 years to present, I've extracted another data set that shows this period from a little bit more detail. And while you can see some fluctuations in temperature, it's fairly stable, and it's marked by these warm periods in the last 3,500 years, but a gradual decreasing of the peaks of these warm periods, leading to the Little Ice Age, which is quite a cool period between about 250 to 750 years ago. And that's when they found that the permafrost had formed in the Barrens of northern Manitoba. And that was interesting to me because it shows that permafrost is the result of quite a recent cooling. And I'll come back in one of my case studies looking at some of the work we're doing near the southern fringe of permafrost, where some of the permafrost features may actually have formed quite recently due to degradation of this fairly young permafrost. just to sort of add to the story, we're currently doing some work down in northern Ontario, looking at peatlands for a road project, and we were able to collect a sample of wood from the base of a 4-meter section of peat, and that wood was dated at 8,000 years before present. And so if you look at this graph where you've got this warming period, that coincides to this point on the graph. And that's when the land emerged in Hudson Bay. So the ice melted back, the Tyrrell Sea flooded the area. And as the land emerged from glacial lake rebound, isostatic rebound, then vegetation began to grow on the land surface. So we see evidence here that indicates that occurred at 8,000 years in this curve, and we also see that from the dating of our sample of wood in the peat. Other people have also dated the development of vegetation on that post-glacial surface in the 4,000 to sort of 7,000 range, depending on your proximity to Hudson Bay. So it paints a picture of temperature warming, the ice melting, land emerging, vegetation forming, beginning to grow at about 8,000 years ago, peat accumulating over 8,000 years, and then permafrost forming within that peatland, something like 250 to 750 years ago. And so that permafrost in this area is quite a recent development, and it continues, as the temperatures continue to warm now, that permafrost is subject to degradation. So that's a little background on the distribution and some information about this the history that has led to the formation of permafrost in some regions, and the timing of that, which in some cases, in some areas, is a fairly recent phenomena. And when we use the term permafrost, it may not necessarily be there forever, depending on what the temperatures are and the climate is like that changes over time. So I'll turn now to what are some of the features that we can see in the landscape that indicate to us permafrost. This image that I show here is an area of bogs and fens in northern Manitoba. So these string patterns are in string fens where you've got accumulation of peat and groundwater moving within the peat. And so the movement of groundwater keeps permafrost from forming because you have water that's above 0 degrees. Within these peat plateau bogs, we can infer that they're cored by ice because we see these areas, these what are called collapse scars, thermokarst features, which form as the ice thaws and the ground collapses. So these collapse scars are a permafrost degradation feature that you could use to infer that this peat plateau bog is actually cored by permafrost adjacent to the string fens. Ice wedge polygons. So these are polygonal patterns that form at various scales and various sizes in the landscape, where the ground contracts either due to thermal contraction or desiccation. Water begins to accumulate within the cracks, and season by season, year by year, there's a wedge of ice that forms that becomes wider and wider. And so you have crack that forms, water infiltrates into that crack, and over time it widens, and you develop these very distinctive polygonal patterns. In some cases where there's ice present in the ice wedges, they are positive features, and there's depressions in the middle of the polygon. Other cases where the ice within the ice wedge polygons is thawing, the zone where the ice wedge was becomes a negative feature and the center is positive. And so you can get a variety of patterns. In some cases where you have a basin, you may get a sort of a concentric and radial pattern, but very distinctive features that indicate that you're in a permafrost environment. Interesting here where you can see there's been a disturbance by a trail, and that's one of the characteristics in permafrost terrain. Very sensitive to disturbance, so if you disturb the surface, you can initiate thawing, which then melts the permafrost and creates a lasting feature on the surface. In these maps, you'll see I've got most of them, I've got the general location of where this image is from. Just other examples of the expression of ice wedge polygons. As I say, often where there's been a drained basin, you form sort of a concentric pattern of polygons around shoreline positions as the basin drained, and then additional features that run radially or perpendicular to that shoreline feature. Here they're very strikingly rectilinear on the upland. These features here are beach ridges in a glacial lake shore zone. Thaw basins, which I've got some other examples, but where you have degrading permafrost, you see the thaw basins. You also see thawing ice wedge polygons. Here you have both some polygons that are thawing and others that are form ridges, and the area in between the polygons is depressed. So different patterns of polygonal features, different densities related to the soil type, the drainage conditions in a particular area. A very extensive expression of them here. I've got other examples. One of the other things we'll see is beaded drainage, where you get thawing of permafrost along the drainage way, usually at meanders where there's an undercut bank, so there's an exposure of the ice-rich permafrost, which creates an opportunity for localized thawing, and so you get these thaw beads along the drainage feature. An example here where we have ice wedge polygons, but also something that are called pingos. And so these are ice cored mounds where the ice within the mound accumulates over time, and the mound grows upwards, pushing the overlying soil up with it. And sometimes you can see the soil begins to break open at the top, and that can lead to thawing of the ice core. You notice that these mounds are within depressions where you have standing water, so you need a source of water that feeds in to allow the growth of those mounds. And so one of the things that you can look for is this association of landforms. So there'll not just be one feature that indicates permafrost, but there might be two or three in the same area. Here you can see that these ice wedge polygons are largely confined to the lower, more poorly drained basins and the elevated ground. Although right here, where I put my cursor, you can see some polygonal patterns as well, which are on a different scale than the adjacent ones in the depression. So different forms of expression depending on the drainage, the soil type, and the local setting. Pingos. So here's a photograph, several tens of meters high, and it's eroding on the surface. It's kind of sort of breaking open gradually over time, but a large ice-cored mound within a wet depression. You can see some ice wedge features adjacent to it in this oblique image. Here's another, well, this is the same. So this is an air photo showing this same feature at a different time and stage. Different settings where these features form. The ones here where you've got a body of water, unfrozen ground, and then permafrost forming above this talc, and an ice lens forming above this remnant of unfrozen ground, and that ice lens grows over time as moisture enters the system and adds to that growing ice lens. Also an open system P.Eng where you have groundwater flow that's delivering water to the ice core that's growing over time and developing this P.Eng. So in this case, you can see all of these are approaching the point where the ice mound is going to become exposed as it breaks through the surface. This is a collapsed P.Eng. So what happens is as that ice becomes exposed, then it begins to melt, and so you're left with a ring with the mound, what's left of the mound, and the ice that formed the core of the mound is now thawed, and so you're left with this collapsed. It's called a collapsed P.Eng. Here again, you can see these ice wedge polygons in the depression that is around or within which that P.Eng. formed. And beaded drainage. Here again, you can see this creek, instead of being a nice uniform channel, you have these widened areas at these meander bends where the permafrost is thawing, and you're getting collapse of that ice-rich zone, forming a wider creek, a channel at the bends of those meander bends. Pattern ground. So you've got, with freezing and thawing, you have an annual sort of uplift of particles during freezing and then thawing in the summer season, refreezing. And so the larger particles get pushed up through the material, and when they reach the surface, they sort of roll off to the side. And so you can get a segregation of the coarse material from the fine over time, and sort of looks like a polygonal pattern, but they're not ice wedge polygons. They're actually this patterned ground. Here, this image you can see adjacent to it, which shows just many of these small circular pattern ground features. On a slope, they may move down slope as well. So instead of remaining in a circular shape, they form these sorted stripes. And so here you've got sorted stripes where it's actually segregating the material based on the density and the gradation of the material. So you get the different rock types separated out. In these upper photographs, you have these circular features that form due to the segregation of the particles within the active layer. Thermokarst terrain. So thermokarst, we talk about karst features in limestone. This is sort of taking that same term, but applying it to karst features that form where the ice-rich, or the ice within the ice-rich permafrost melts. And so it's an indication of degradation of the permafrost, of sort of conditions where the permafrost is now starting to thaw. And you see areas like this, which is off northern northeastern Manitoba, where you have this very extensive pattern of fall lakes. And so there's some large and some small, and then with some streams running along between them, but just a very, very diagnostic, very distinctive uh, pattern of lakes, which creates quite a challenge if you're looking at building some linear infrastructure across an area like that. Very, very, very difficult. Another example, a black and white air photo. And so within this area, there may be remnant permafrost still remaining around these thaw lakes. And so those, and often there'll be talics. Remember, to start, I defined what talics are. So you have unfrozen ground below the thaw lake, and then frozen material, frozen ground below that, down to the permafrost base. In some cases, on the larger, deeper lakes, that unfrozen zone may extend continuously down with depth, and there's no frozen ground remaining. So you have a through going talic versus an open talic. As that process occurs, as you have warming conditions, you begin with an active layer sitting directly on top of permafrost. As the conditions warm, the first sort of step is for the active layer to extend down to greater depth. And as it extends down to greater depth, it reaches a point where there'll be an unfrozen zone that is below the active layer. So the active layer still forms freezing conditions down to some depth, unfrozen, and then the permafrost is below that. The talic increases in depth over time to the point where you have all unfrozen ground, and all you have in terms of frozen conditions are the seasonally frozen conditions near the beginning, in which case it's no longer called an active layer, then it's the seasonal frozen layer. And so that's kind of depicted here as well, where you have a small shallow lake that forms with permafrost at its base, somewhat deeper, small deep lake, which has unfrozen ground below, and then the permafrost in the larger, deeper lake where it's unfrozen all the way through. In some cases, the fall lakes will drain, and so you're left with a drained fall lake basin. And so you can see both here. You can see thaw basins that are still inundated with water, and you see many others in this case where the water has drained. And once the water drains, you may, depending on the conditions, the ground may freeze again, at that location. One of the interesting things about the thaw lakes is that in order for them to drain, they need an outlet. And so you can, when you're looking at them, you can always find an outlet where they've drained into an adjacent stream. And so they're sort of like beads along a string. In some cases, where did I see one? This one, which is a once removed, but it drains through this basin and then into the stream, as does this one. And so you can see these drainage outlets at each of these drain thaw basins. Not a permafrost feature, but here you can see these raised beach ridges that formed as the land rebounded during deglaciation. Oriented thaw lakes, so that's another kind of variety of thaw lakes where there's a a persistent wind direction that promotes thawing of the permafrost in a preferential direction that's aligned parallel to that prevailing wind direction. And so you see these long, narrow thaw lakes as opposed to these very nice round lakes elsewhere. But still, thaw lakes, a very dense concentration of them here. Collapse scars. So I had this slide earlier, and so I've already spoken a little bit about recognizing these collapse scar features, which are diagnostic of permafrost being present within these peat plateau bogs, and then the string fens where you have no permafrost. So very sharp boundaries between these landforms. And so you go from non-permafrost conditions to permafrost conditions. And then within these collapse scars, of course, the ice is melted. There may still be some permafrost at depth, but there's been enough thawing of the ground ice within the permafrost to create a collapse feature. One of the terms that Dr. Mollard would use is speckled bog. So you have these bogs, black spruce on them, and the speckles are caused by this thermokarst process that creates the collapse scars. And so you've got a nice, so very diagnostic. So you have the black tone here is from black spruce, which likes to grow on the bogs, and you have these white collapse scars. So permafrost remaining within that bog, and SF is for string fen, and so no permafrost within the string fen because you've got an active groundwater gradient, active movement of water that's above zero, and so there's no opportunity for permafrost to form in that type of landform. But throughout this area, you can see these speckled bogs all across this photograph, just north of Lake Winnipeg a bit. Here's a photograph that I took along the lower Nelson River. We were doing studies looking at dam sites on the lower Nelson River from Manitoba Hydro. And so you can see this cracking, this caving of the peat around the collapse scar. So as the ice melts, you get subsidence, and around the perimeter, that subsidence is showing up as sort of cracking and collapsing of that peat into the collapse scar. So very, very distinctive. I don't really see any examples here, but sometime if you've got a tree along the margin, you'll see the tree is toppling, falling into the collapse scar. So you've got an ice lens that's formed. As the ice melts, you're left with a collapse scar depression. This is an interesting one, and it's in this area in southern northern Ontario that we're working on a project right now. And this is a photograph that I took in 2002 of what I thought was a collapse scar as we're flying over the area. It's in an area of isolated permafrost, so you're not expecting to find very much, but you can see in these images you have these features that to me appear to be collapse scars. Now there's still a question about whether there's any ice, any permafrost remaining, and as that may be a remnant of permafrost, but the permafrost may have all thawed. So I got the set of older air photos, so 1967 photos, and I was looking at, so this feature is right here, which is right here. And so in 1967, you can see that there's no collapse scar feature. In the 2015 image, you can see that it's there. So my conclusion is that sometime between 1967 and 2015, the ice core, the permafrost there thawed and created that collapsed scar. We have some drilling planned, which we haven't conducted yet, where we want to put a hole on the rim of that, just off the rim of that collapsed scar, and one in the middle of it. And I'm expecting the center to be thawed. If there is any ice permafrost remaining, then I would expect there might be some around the rim, but that's what we're trying to establish. You can see other features that where there's been a what I would interpret to be a collapse scar visible in 1967, and of course there's still some evidence of that now. So it's an area where there's where it's near the southern margin of the isolated permafrost zone. Evidence that there has been permafrost, that there's been permafrost degradation, and some uncertainty though as to whether any permafrost still remains. And I'll come back to that in one of the case studies at the end. Beta drainage. We mentioned that several times already with ice wedge polygons in the adjacent area. Different expressions of beta drainage, but quite distinctive once you've seen it, and again associated with ice wedge polygons in the adjacent area. You can see where it got the name. Look interesting here. This is in Alaska, where they built the airstrip over permafrost affected ground, ice wedge polygons in the area as well. Horsetail drainage. So in areas of continuous permafrost, very essentially no infiltration. So all of the runoff is over the surface, and so you form these very fine patterns, which are called horsetail drainage on slopes. So another indication of permafrost. Here's another expression of that. Others here. Pattern ground, we've already looked at quite a few examples of ice wedge polygons, soil stripes here in this example. The other thing here, where we're really in the far north in continuous permafrost, the sort of lack of any tall vegetation on the landscape. Here you can see the bedrock strategically in the slope, these large alluvial fans. Solid fluxion, so some mass wasting features. This is a creep feature within the active layer. So you see these little ripples on the surface. That's indicating creep within an active layer in permafrost. You can see them here on the slope. Other examples as well. This is in the Rocky Mountain House area in Alberta. Additional examples. So they're quite distinctive little scarps, little steep scarps, and often you can see a number of them as you move down the slope. Thaw flows, thaw failures, where you've had thawing of ice-rich permafrost, saturated sediments flowing down slope. So you've got quite a large failure bowl, a very narrow failure channel or failure chute, because the material is essentially liquefied and then flows and spreads out below. So very diagnostic shape to these thaw flows. Here you can see quite a large number of them in this image, in amongst other permafrost features. So you can see quite extensive thaw failures in this area. These can advance, retrogress very rapidly. These two images are just taken 1 year apart. And so this is where the scarp was in 2010, and this is where it is in 2011. This is the 100-meter scale, so it's gone back something like 50 to 75 meters within that one year. Two profiles showing the change in the scarp position and the depth of the failed zone. Active layer detachment. So these are very thin, very shallow failures within the active layer, where you have frozen ground underneath the material. The surface is saturated and flows down these very narrow channels. These are in northern Manitoba, where there was a forest fire, which promoted thawing of the permafrost, which led to the saturated conditions. And so you had a whole series of these active layer detachments along the valley side, along the lower Nelson River Valley. And you can see these formed just very recently, and the debris is still present in the nearshore zone of the river. Rock glaciers, if you have talus slopes that are saturated and that the water is frozen and has permafrost, these talus glaciers will gradually creep. The ice is ductile, and you've got this saturated talus, and so it will form these ripples of frozen material creeping down slope, very slowly, but very persistently over time. This is the sheep, the national park. Sorry, just lost the name. Kewaunee National Park in Yukon, and we're doing field work looking at debris flows coming here, which are not necessarily related to permafrost, but in the same area we have a rock glacier. That's the map of the debris flow area and the rock glacier here. So watching my time a little bit. Engineering implications, I won't speak too much about that, but as the ice permafrost thaws, you're left with very poor ground conditions, a lot of disturbance, construction, poor foundations, aggregates in permafrost areas. It's interesting, if you've got an esker that's frozen, very difficult to excavate, and so they'll often allow it to thaw and then excavate it layer by layer as it thaws. Environmentally, of course, pretty sensitive to thaw. If you introduce some infrastructure like a pipeline or a building that interrupts the underlying permafrost, creating a source of heat, and it's not insulated and not kept cool below the foundation, then of course the permafrost thaws and results in differential subsidence, collapse and thawing of the ground around the pipeline. And so there's methods for insulating the foundation, insulating the pipe, thermal siphons to try and maintain the ground in a frozen condition. Soil heave, which is related to capillary action, ice lensing, and heaving as moisture gets into the pore spaces, and then that moisture freezes, the ground heaves, and it's much more of an issue in clays and silts than in sands and gravels, which are better drained. And so there's a chart here showing how the silt sizes are the most susceptible to frost heave as compared to more permeable granular materials and less permeable clay materials. A couple of examples in reservoir shorelines showing permafrost thaw around reservoirs. So if you build a reservoir, the water begins to thaw the sediments around the reservoir. Here we see thawing underneath frozen till in the Long Spruce Reservoir. collapse and failure of the banks related to permafrost thaw in Stevens Lake. This is that one that I showed you at the beginning with the thick ice lands within it. We came back a year later and that had completely melted. And so all you were left with was the superficial peat that had collapsed into the reservoir. I want to quickly run through a couple of case studies if I've got time. Is that all right to carry on?
Yeah, we have about 10 more minutes. Maybe we can give a couple of minutes at the end for questions if there's any.
You bet. I'll try to. So this is an area in Northern Ontario where our project runs from the non-permafrost area through the isolated into the sporadic. And so we're interested in whether to what extent there still might be permafrost remaining in these areas. And so we mapped these, I mentioned this collapse scar. There's other collapse scars that we identified that have become treed. And so we mapped 1,700 collapse scars along our project and looking at two sets of imagery that were about 60 years apart, whether those collapse scars were increasing in size, stable, or decreasing. And it was interesting to see that the majority of them are stable. So the orange bars are the collapse scars that are stable. The gray are ones that are decreasing in size, and the ones that are decreasing in size are more towards the south, and the ones that are increasing in size are more towards the north. And so it seemed to be evidence of gradual kind of warming and degradation of the permafrost from south to north, but that to a large extent, they've remained stable over that time period. The other case study that I wanted to just share with you quickly is looking at a road route from Rankin Inlet to Baker Lake. So here we're in the continuous permafrost region, and some of the kind of permafrost features we see in that area. We have the ice wedge polygons, quite large scale polygons. Here you can see them infilled with water, so they're degrading, and an existing road that crosses some of those. And LiDAR, I mentioned LiDAR in the title, so I've got a few hillshade images here showing how those ice wedge polygons really show up very distinctively within the LiDAR imagery. Different types of features depending on the type of terrain you're in. Some very long features that extend over quite a distance and intercepted by others at right angles to them. Thaw failures. So here there's a couple of failures, and you can see how those are expressed within the hillshade imagery. This is what the water looks like in the LiDAR imagery, and these failure scarps along the slope. So failure occurring along the slope of this permafrost ground. Others like that. Sorted circles, beautiful examples of sorted circles in that area. Many sorted circles together. Polygons in the low areas, sorted circles in the upland. Other expressions of permakarst features, patterned ground in the imagery. Slope failures. I wanted to leave you, though, with a couple of shots from Mars. So a number of years ago, Dr. Mollard was recruited by a geologist at NASA to look at features on Earth that they were seeing similar types of features on Mars. And so one of those is permafrost features. And so here we see failures, slope failures on Mars that look very much like the ones we just looked at in Nunavut, patterned ground, polygonal patterns, pingos. And look at this amazing pattern of ice wedge polygons on Mars. So this is 5 kilometers across, this image. And so if we look at a section taken out of that, this is 1 kilometer across. So these are about 100-meter squares, these polygons, and then within them a much finer pattern of ice wedge polygons. So we can take what we see on Earth and use it to interpret images on Mars as well. So I've taken you through sort of the regional distribution, something about the timing of ice formation, permafrost formation, and degradation, and then showing you a range of features that you can use to identify that you're dealing with permafrost in an area, some idea of whether it's degrading or not, and at what rate. That can be useful for baseline mapping and studies related to engineering and environmental projects. So I'm going to stop there then, and hopefully left a little bit of time for questions, but you have some questions there that you want to share with me.
Yeah, thank you so much, Lynden. That was great. You showed us some great air photos and LiDAR images. It was very interesting, especially the ones from Mars. It's really amazing. We do have a question. Will even the smallest disturbance, say walking or driving an ATV, on the permafrost express itself on air photos or LiDAR years later?
It really depends, I guess, to what extent that disturbance disrupts the kind of the insulating layers, so the vegetation and the soil horizon that's overlying the permafrost. So I could imagine that walking or a very light ATV might not, be impactful if it doesn't sort of break the surface and doesn't cause enough compaction that it allows the insulating factor that's above the permafrost to be affected. So there would be some threshold there where I think you would need probably something more than just walking across the area. If you had a ATV and it was during the summer season and the surface is kind of wet and you create ruts with the ATV, I would think that would probably be enough to destabilize the permafrost. And then once it starts to thaw, then it can grow. And so even, if some of these collapse scars form because a tree falls over and exposes the root area to more solar radiation, and then that grows over time. So it is very sensitive in that way for sure.
Great. While if you have any other questions, feel free to post in the Q&A box. While we wait, maybe I can ask a question. Do you think that with increasing climate change, it can be difficult to sort of use the permafrost indicators to inform long-term decisions regarding construction or design?
Yeah, I think to me the permafrost, being able to identify those features is really the first step in sort of knowing that you're dealing with permafrost in an area. Especially, and it's very useful to look at historical imagery. So with the northern Canada, there's often aerial photographs that are available from the 1950s. And so that's getting to be now, 75 years of history. And so you can look to see whether there's been a change in some of the features. And so if you're seeing, ice wedge polygons that are visible in the 50s and then now they're wider or they're larger, or like this collapse scar that I noted in Northern Ontario, it indicates that there's been some degradation over that time period. And with, conditions being, average temperatures being warmer now than they were, say, 50 years ago, one could only imagine then that rate of degradation is going to potentially increase in the future. And so it's getting to the point I've heard, people talking about, making a decision about whether it's feasible to try to maintain the permafrost as in place, or do you have to plan for actually the permafrost to thaw and design your project accordingly? Just given how things have been going.
Yeah, yeah, of course. Well, we are at time. Thank you so much, Lynden, for today's presentation. It was very insightful, I'm sure, for everyone. And if anybody has any questions that comes up later, you can either reach out to Lynden directly or you can email it to us and we can make sure that that reaches Lynden. So thank you so much. Thanks, everyone.
Yes. Yeah. Well, thanks for the invitation, and wish everybody well.
Yeah.
Thank you. Yeah.
Thank you.
Bye-bye.